You know for a long time how to calculate areas below graphs. But until now, the shapes of the graphs were very simple shapes, and you could use the formula for whatever shape you had to calculate its area. So if it was a straight horizontal line, you would use the area of a rectangle. If you had a straight line up, you would use the area of a trapezium. If you had two lines like this, you could use the area of a triangle, and so forth. Or you could break these down into smaller areas whose shape you would recognize and use the corresponding formula to get the overall area. But now the question is, what if you have a function that is not a straight line, such that this random line that I just put here kind of looks like a trapezium, but it's not. So there is no known formula for you to calculate the area underneath it. So we need to figure out a mathematical way of finding the area, because it should be possible. There is an area. Okay. So what is the method that was eventually discovered or invented? The area of this shape can be approximated by doing what you can see here. All right, I'm going to expand this so you can see a little bit better. I broke the area down into smaller rectangles whose area I can easily determine, right? You have here a rectangle, and the area of each individual rectangle is going to be given by the width of the x-axis and the height of the y-axis. So it's going to be this times that, right? In this particular case, it's going to be y1 times this horizontal width over here, which I called delta x. All right, I think that I already mentioned this before. Let me put this bigger. This is lowercase delta. You may remember delta from other topics or subjects. Delta is that triangle, that Greek letter triangle. Usually represents in math, in the context of math, it represents a difference, a big difference. Now, the lowercase delta, this one over here, represents a small difference, okay? In this case, the difference between this point over here and that point over there. And if you see, I made here, I don't know, 12 different rectangles, and I always have put underneath each one of these rectangles the same width, delta x. So the width of every single rectangle over here is the same. It's tiny, and because of that, it uses the lowercase delta to represent that small difference between one point to the other. And then the height is going to be the height corresponding to the point where the rectangle will hit on its left side the function itself. Okay, you can see this from the drawing I see. And if you look at the area that is shaded here in yellow, you can tell that the area of this is close enough to the area underneath this curve and between points over here O and point over here P, right? It's not quite, but it's close enough. You still have these little white gaps over here, but the area is close enough. Close enough. What could you do in order to approximate the area of these rectangles closer to the true area underneath the curve? If you think a little bit, I think it's easy for you to understand that if you bring this delta x even smaller, all right, the size of these gaps that are still missing are going to be smaller as well, right? Instead of having 12, if instead of having 12 rectangles, you would have, let's say, 24, if you double the number of rectangles, these areas over here that are not contemplated by the area of the rectangles would be smaller. And if you add the areas of all these 24 rectangles, the overall area is going to be closer to the real area that you are looking for. All right? But one thing is for sure, no matter how many rectangles you use, the area that you are looking for, which is the actual area between points O and P, is always going to be a little bit bigger than the sum of all these areas of these rectangles. Okay, what is this? This is the area of rectangle 1, this is the area of rectangle 2, the area of rectangle 3, etc., until the area of rectangle 12. As I've told you, delta x is the same to all rectangles, so you basically can factorize this. That's what I did in the next line. So I factorized delta x, and I just put the sum of all these heights over here. Okay? Needless to say, I didn't bother to say it a little while ago, but I'll say it anyway, that if you have the expression for this function, it's easy for you to get the value of y just by substituting the value that you have in each one of these points on the function, and you get the corresponding value of y, right? So you are adding all the values of y and then multiplying by delta x, which is the same for all rectangles. And you know that whatever value you will have here is going to be close to the area that you are looking for, but still a little bit smaller. All right? How can I represent this in another way that you already have seen before? I have here a sum of 12 different values I can represent by this symbol over here. This symbol over here represents the sum from 1 to 12 of all different y's times delta x. As I mentioned before, if the number of rectangles n increases, the width of each rectangle, delta x, will decrease, right? And the area given by the sum of these rectangles gets closer to the true area. And this is the part where we are leaving this symbol over here. We are leaving what we learned before about adding stuff and go to the part of integration. Because now we are going to use the idea of limits again. Don't forget that I already brought this up on the first lesson about differentiation to explain how differentiation worked. You needed to understand this mathematical tool, which is the limit, which enables you the whole process of differentiation. This will enable also the whole process of integration. So let's say that n, don't forget that n represents the number of rectangles that you are using, tends to infinite. So instead of having 12, 24, 100, 1000, 100,000, you have an infinite number of rectangles. Then if you have an infinite number of rectangles over here, what is going to be the width of each one of these rectangles? It will tend to 0. That's what this means. When n tends to infinite, the value of delta x tends to 0, right? In this case, for each value of y, there will be a corresponding yn, and therefore the sum of this infinite number of rectangles is the area between y and the x-axis. If the number of rectangles starts increasing and tends to infinite, the delta x will tend to 0, but if you still manage to add them all, then you can be sure, as this tends to infinite, that the sum of all these areas will be not smaller, but equal to the area that you are looking for. Mathematically speaking, how do you represent that? You saw this already, as I mentioned, when I taught differentiation. You have the limit when n tends to infinite of the sum of all y's. This is the same thing I used over here. The sum of the height of all rectangles as you add from the first to n, okay? N, don't forget, tends to infinite, times the delta x. Delta x being the width of each rectangle that will now tend to 0. Now, I'm going to do a pass of magic over here. There is no point for you to know how this was done, but the thing is that whenever this happens, this symbol stops being this that you know for a long time and becomes this over here. This kind of elongated S, and the reason why it looks like an S is because this is indeed a sum, the same way that this corresponds to a sum. All right, but now it's a sum of infinite tiny small width rectangles from 0 to point P, and this is going to give you the area between y and the x-axis, between the points O and P. All right, and from the previous lesson, from lesson 1. You already know how to integrate. So here you have a way to calculate areas underneath a curve, no matter what the curve is. More interestingly, you can apply this. This is general enough to be applied to the straight lines that you already knew how to calculate the area of, and it will give you the area corresponding to the formulas that you were using for the trapeziums, for the rectangles, for the triangles, etc. You could use, if you have a shape that you can recognize, you can either use the process that you learned a long time ago using the areas of the formulas for the areas of those shapes, or you can use this general expression. You will still have the same result. Now, let's go to more details about the areas. All right? Let's say now that you want to calculate the area of this shape, okay? Doesn't matter what the function is, I just call it f of x between points A and B. Again, I'm talking about the area between the function and the x-axis. All right, you have these points over here, A and B, which correspond to the x coordinates of A and B. All right, so I want the area between the graph, the x-axis, and points A and B is given by this expression over here. All right, you have something that is different over here, which are these 2 points, A and B. I'm kind of off frame. I wasn't paying attention. Maybe I was for a long time. I'm sorry for that. So these points A and B are the x coordinates of points A and B, uppercase. All right. So how do you do this? How we are going to integrate, but just between these 2 points? Well, the process is here explained. First, you have to integrate f of x, the way that I assume you already know, okay? Just integrate it as normal, all right? And you will get an expression for the primitive, all right? Then what do? Then, on that expression, that mathematical expression that you will get after integrating f of x, you are going to substitute x by b, and you are going to substitute x by a, and you are going to subtract them to the biggest from the smallest from the biggest. You represent mathematically this difference as this. You have here the expression for the primitive that you get again after integrating f of x, and you write the limits of integration over here, the a and the b, and this means this. There is, I don't think I've written this. There is no need for you to worry every time you have limits of integration. There is no need for you to worry about the value of k, all right, the arbitrary constant. Why? Because let's imagine that you would worry. If you put it, there's no problem, because you are going to write it here, okay? You'll find the primitive, and you are going to have whatever k is, you will write plus k, but you are going to get it again over here. And this minus is going to subtract this k, so you'll have k minus k. So it cuts out. Every time you are doing integration with limits of integration, you don't need to worry about the arbitrary constant, because by the nature of what you're doing, the arbitrary constant is going to cut out. All right? But what happens if you have a function like this? It goes and crosses the x-axis. It can happen, right? But you have to pay attention to these cases. In some situations that appear in some exams, you are not told explicitly that this will happen with a function. You are not given the shape. You'll have to figure it out yourself, or the question has given you already hints that it is crossing the x-axis. And in that case, you have to pay attention, because if you would calculate the area of this part over here, the one that is that crosses the x-axis, is on the negative side of y, you will get a negative area. Okay, if you apply this rule, you will get a negative area, right? And you cannot have negative areas, right? So there is a mathematical trick. I mean, it's not a mathematical trick. It's just one thing that you have to do and worry about. Every time you have a negative area, just turn it positive. As simple as that, all right? But you have to be aware that the function will cross the x-axis and will eventually go to the negative territory of the y-axis, in which case you have to break this down into two smaller parts, right? So if you want to integrate a function such as that between a and b, you have to separate it into bits, from a to c first, and then from c to b. Now, then you can integrate each one of these parts as normal, as explained before. And if eventually you have one of them that is negative, just turn it positive and add them. Okay? If you want the area again, you want the sum of its parts, and being areas, you don't have negative areas. What if you want the area between two curves? Let's say that you have this function in blue and this function here in orange, and you just want this bit over here in green. Well, I think you already have practiced, not in this chapter, obviously, it's new, but you already dealt with something similar last year in not in coordinate geometry, in a chapter about trigonometry, in which you'd have to calculate areas that you would get by subtracting a smaller area from a bigger one. That's the same thing that you have to do here. So the concept is what? Well, just calculate the area underneath the biggest function, the one that is up the x-axis, and then calculate the area of the function that is closer to the x-axis, and substitute the latter from the first. That's what I have over here. Okay. This is the area of the blue one. This is the area of the orange one. Subtract one to the other, and you have the area that you want. The concept is very simple. You just have to integrate twice. But now that you know the tool, how to integrate, now that you know how to integrate by parts, this shouldn't be complicated. Actually, this chapter, if you understand the concept of integration, the first lesson to begin with, you will very quickly learn how to use the tool, and then everything is going to be kind of straightforward. More things that can appear, not very common, but it can happen. Actually, it can be kind of common, to be honest. I would say that in 30% of the exams, you will have this situation. Calculating an area between a graph, and not the x-axis, but the y-axis. I guess that if I would ask you to give your educated guess on how to do this, if you think a little bit, I think you would get it, right? If you are focusing on getting the area that is to the left, that is between the graph and the y-axis, what is the trick that you would use? Well, you already learned this previously. This is going to be calculated using the inverse function, right? If you use the inverse function, then you are putting this in relation to y, which is exactly what you are looking at this moment. So what do you have to do? You have to calculate the area between a and b. Don't forget that the limits of integration are no longer on the x-axis, they are on the y-axis. But instead of writing f of x, you write f of y. And what is f of y? This is the inverse function that you already learned how to determine, right? So to calculate this, you'll need to first start with the original function, f of x, and find an expression for x in terms of y, right? What is this? This is the expression for the inverse that you already learned how to do before. Then just integrate it as normal. Integrate f of y to find its primitive, capital F of y, and then just substitute b and a on the primitive, just like you did before over here. The only thing is that, like you have done over here, okay? But instead of focusing on x, you focus on y. As simple as that. You just have this extra step of getting the inverse. And in case you are not given these values a and b, in most cases you will, you just have to determine them by substituting. You will have instead the x coordinates of points A and B. Just get the y coordinates first. You'll know the limits of integration of this, and then just apply this rule. This is as complicated as I can think of. Find yourself finding the limits of integration there. Okay? What if you have situations, this is even rarer, if you have situations in which you just have one limit of integration, a function such as this one. It goes on forever. It tends to go to 0, the y coordinate, but it never actually touches. But the area is going to be a finite value. Although the function is infinitely long and ever closer to the x-axis, the value of this area tends to a specific number. In this case, you'll have to use the concept of limits. Again, it's just a mathematical way of representing something that is simpler, in a procedurally simpler than it looks if you look at the notation that you'll have to apply. Okay? A shape such as this one will be of a function such as this. A constant over x to the power of something. All right? And this n is a positive constant, right? The bigger x is, the smaller the overall value is going to be. So this explains this overall shape. And you are basically integrating between point A, whatever A is, and the infinite. But you cannot work with infinites, right? So what is the trick that you use? Instead of infinite there, just put the letter b, for example, and then write before the integral sign, limit as b tends to infinite of the function. Then integrate this as usual. All right? Don't forget always in each step to write this stuff. Limit as b tends to infinite. Limit as b tends to infinite. And then everything else just works as normal, right? You are just doing here what you have done before, okay? Applying the rules of integration between points A and B. The only thing is that this b is a theoretical b that basically corresponds to infinite, but this is written before. You just carry on this notation until the end of the procedure, and eventually you get here. And now is the moment when you are going to get rid of this. You are going to get an expression such as this one. And now, what happens if b tends to infinite? If this tends to infinite, the denominator is going to be infinitely big, and what is going to happen to the value of the fraction? It's going to be 0, right? So you're going to end up with that part. Don't forget, N, A, C, all of these are going to be numbers, and you are going to have a number. This is much easy to do than to watch. This seems complicated. It actually isn't. The only thing that you have to do that is extra work is substituting the infinite by a letter and writing before that limit as that letter, I picked b, tends to infinite, and then work as normal. And once you have an expression with that letter, with the b, put infinite there, see the result. Usually that's going to be 0, and you are going to be left with whatever you have there.